Today we're going to discuss limits at infinity. Limits at infinity should be fairly straightforward for you, but they aren't for everyone, so let's step through it one at a time. First, we'll start with the theorem. If r is a positive rational number and c is any real number, then the limit as x approaches infinity of c divided by x to the r equals 0. Furthermore, if x to the r is defined when x is less than 0, then the limit as x approaches negative infinity of c over x to the r is also 0. How can we use this particular theorem? Let's look at a couple of examples. First, we're going to find the limit as x approaches negative infinity of 5 over x minus x over 3. We have properties of limits that allow us to take the limit of a difference. So the limit as x approaches negative infinity of 5 over x minus x over 3 is equal to the limit as x approaches negative infinity of 5 over x minus the limit as x approaches negative infinity of x over 3. Using the theorem for this one, we find that this limit is equal to 0. A real number divided by x to the first power. As x goes to infinity, my value becomes 0. Subtract. My second limit as x approaches negative infinity. Although negative infinity is not an actual number, it's a symbol for all numbers smaller than any number you can think of. If we were to evaluate, we would have negative infinity over 3. Thinking theoretically and not as an exact number, if we subtract negative infinity divided by 3, subtracting the negative makes a positive infinity. Whether we divide it by 3 or divide it by 300, it's still going to be a very large number. This is our answer. The next example uses radicals. If we want to find the limit as x approaches infinity of the square root of the difference x squared minus 2 divided by 6x minus 7, we need to keep in mind that the power of x inside the radical and the power of x outside the radical might not necessarily match even though they're the same size. So keep in mind that x is equal to x squared inside a radical. Technically, we should put absolute values here because the square root of x squared is actually equal to the absolute value of x. Since we're going to positive infinity, we don't need the absolute values as much. To use this theorem, we're going to divide each and every term by the highest power of x in the entire expression. We have to consider the radical in deciding what that highest power is. In this particular problem, x on the outside of the radical and x squared inside the radical are actually the same power. So when we divide each term, inside the radical we're going to divide by x squared, whereas outside the radical we divide by x. Inside the radical, square root of x squared is equivalent to outside the radical x. Simplify these. X squared over x squared will give us 1. Minus 2 over x squared, not much simplification that can be done. In our denominator, 6x divided by x will give us 6. Minus 7 over x cannot be simplified. Notice that each time I have rewritten the limit. I will rewrite limit until I actually let x go to infinity. I must keep writing this until the limit is taken. As we evaluate this, we now have properties of limits that will allow us to go inside of radicals, to allow us to pass through the difference, divide as well. The limit of a quotient is the quotient of the limits. So I can take a look at these individually. As x goes to infinity, 1 doesn't really care. There's no x involved, so that limit is 1. As x goes to infinity, 2 over x squared, this is where our theorem comes in, so it's written in red here, that becomes 0. As x goes to infinity, 6, that's just 6. And as x goes to infinity, 7 over x also becomes 0 due to our theorem. We can now simplify the square root of 1 over 6, and always simplify your radicals if you can. The square root of 1 is just 1, and this limit should be equal to 1/6. In our last example, we're going to have the powers inside and outside not necessarily the same. In this case, we're going to look at the limit as x approaches negative infinity of the difference the square root of the difference, order matters, people, of x to the 6th minus 1 all divided by x to the fourth minus 1. On the outside of the radical, we have x to the fourth. Inside the radical, this would be x to the fourth is equivalent to x to the eighth power. Just a side algebraic note, the absolute values are not necessary here because x to the fourth power will return a positive value. Excuse me, non-negative, it could be 0. This is our largest power, x to the fourth outside the radical, x to the eighth inside the radical. So we're going to divide each term of this expression appropriately. Inside the radical, we're going to divide by x to the eighth. Outside the radical, we're going to divide by x to the fourth. Notice once again, I write the limit until I actually use the limit and send x to negative infinity. As I simplify, x to the sixth over x to the eighth will give me 1 over x squared under the radical. 1 over x to the eighth cannot be simplified, so I write it again. X to the fourth divided by x to the fourth is 1. 1 over x to the fourth cannot be simplified, so I leave it. Now I'll let x go to negative infinity using the theorem to evaluate a 0, subtract another 0. In the denominator, 1 doesn't care what x does. It doesn't involve x at all, so it stays as a 1, minus 0. When I simplify 0 minus 0 and get 0, the square root of 0 is 0. 1 minus 0 is 1. And 0 divided by 1 is equal to 0. Limits at infinity. Keep in mind the different powers on x as your inside and outside of a radical.